Good morning to everyone. I am Francesco Pagliaro, a PhD student from the University of Milan, and my PhD project is about the crystal chemistry and non-ambient behavior of natural rare earth elements, arsenates and phosphates from the Mount Cervandone in Western Alps in Italy. Okay, let's start with a brief introduction to rare earth elements, hereafter Re. They correspond to the lanthanides series, which consists in a group of 15 elements, grouped into light Re from lanthanum to europium and heavy Re from gadolinium to lutetium, on the basis of their atomic weight coupled with decreasing atomic radii from lanthanum to lutetium. Scandium and yttrium, which share a similar geochemical behavior with Re, are often included into the group. Re are widely used in a lot of high-tech applications like hard disk drivers, phones, LCD monitors, batteries, and also lasers, petroleum refining, permanent magnets, and ceramics. The extraction of Re is mostly concentrated in China, which in 2009 introduced export taxes. Due to the high economic importance and supply risk, Re are classified by the European Commission as critical raw materials. In this light, it has become increasingly important to understand the mineralogical and petrological processes responsible for reconcentration and partitioning. During my PhD project, I will focus on the main Re-bearing minerals occurring at the pegmatitic deposit of Mount Cervandone. These are two phosphates, monazite and xenotime, which are two of the main Re-ore minerals, and also two arsenates, gasparite and chernovite. The aims of my study are to characterize the crystal chemistry and the structural features of the four selected minerals, and also to investigate their phase stability and their elastic and structural response at varying temperature and pressure. The obtained results will be implemented in a broader study devoted to understand the minerogenesis of this Re-bearing deposit. The phosphates and the arsenates that I mentioned can be described by the general formula Re(X)4, where Re is a trivalent metal from the lanthanides series, or yttrium or scandium, and X is phosphorus or arsenic. They mostly crystallize in the tetragonal or in the monoclinic crystal system, and both the monoclinic monazite type crystal structure shown on the left and the tetragonal zircon or xenotime type crystal structure shown on the right are composed of rods running along the C crystallographic direction, formed by the alternation of Re-coordination polyhedra and tetrahedra, the arsenic or phosphorus tetrahedra. Besides symmetry, a primary difference between monazite and the zircon or xenotime type structure is the coordination environment of the Re cation. In the monoclinic monazite structure, the larger light Re ion is coordinated to 9 oxygen atoms, whereas in the tetragonal structure of xenotime and chernovite, the smaller heavy Re, yttrium or scandium are 8 coordinated with the oxygen ions. All the samples used in this work are natural phosphates and arsenates from the pegmatitic deposit of Mount Mancher-Bandone, and they are listed in a table. Gasparite and monazite are respectively the light Re-bearing arsenate and phosphate, sharing the same monoclinic structural type. Also, chernovite and xenotime share the same structural type, in this case a tetragonal one, and they are respectively the arsenate and phosphate of yttrium and heavy Re. For all the samples, the chemical composition has been determined by electron probe microanalysis coupled with wavelength dispersion mode, whereas the crystal structure of all the samples has been determined on the basis of X-ray single crystal diffraction data collected at the Earth Science Department of the University of Milan. Up to now, only on Gasparite, the high pressure behavior has been studied by means of in situ single crystal X-ray diffraction performed up to 10 gigapascal at the high D15B beamline at the European synchrotron of ESRF. The figure shows the unit cell volume versus the amount of phosphorus for the chernovite xenotime solid solution, and it is completed with data from previous works. It is clear that chernovite and xenotime show complete solid solution with a decreasing in the unit cell volume with the increasing of the amount of phosphorus. On the contrary, as suggested by our data and literature data, no solid solution occurs between Gasparite and monazite hand members. Regarding the high pressure behavior of Gasparite, the diagram on the left shows the evolution of cell parameters with pressure. In the pressure range under study, no phase transition has been observed, and the elastic behavior is slightly anisotropic, with a relatively higher compressibility along the direction parallel to the IA crystallographic axis. Birch-Marnagan equation of state, truncated to the second order, was fitted to the experimental PV data, yielding to a bulk modulus at ambient conditions of 106 gigapascal. As reported in the normalized volume versus pressure diagram on the right, the most important deformation mechanism responsible for the accommodation of bulk compression in Gasparite is the volumetric compression of the Re polyhedron, represented by the red dots, and calculated from the refined structure models. In fact, fitting the pressure volume data for the Re polyhedron with a second order Birch-Marnagan equation of states yields to a bulk modulus of 92 gigapascal. The diagram also shows the evolution with pressure of the arsenic tetrahedron, except for a slightly compression in the lower pressure range. It doesn't contribute to accommodate the Gasparite bulk compression at pressure greater than 3 gigapascal. However, the population of the tetrahedral sites apparently plays a significant control on the bulk compressibility of the monazite-like structure. In fact, the presence of the larger arsenic in place of the smaller phosphorus leads to a bulk modulus 40% smaller with respect to that reported in literature for cerium monazite. The two diagrams here reported show the shortening with pressure, on the right normalized, of the Re-oxygen bonds. It is clear that the Re-O9 polyhedron is a distorted polyhedron better described as an 8+1, and because of the Re-O1A bond length, and this is also the most compressible bond. Okay, in conclusion, the future prospects connected to my PhD project are to study the isothermal high pressure, the isobaric high temperature, and the combined high pressure and high temperature behavior of the 4 selected minerals. In addition, we aim to expand the crystal chemical investigation to other re-bearing minerals occurring at the same site. And that's all. Thank you for your attention.